And now I will define the notion of conjugated elements and classes. So two elements A and B of a group G are said to be conjugated of one another if exists an element S belong to G such as B is equal SA S minus 1. So we call class the set of conjugated elements of one the other. So the class is a very important notion in group theory. Now some important remarks. So the neutral elements of a group form a class by itself. This means that the only conjugated element of the element E is E itself. Because no matter what A belong to G, A minus 1 is equal to E. Now similarly, as if G is an abelian group, each element form a class by itself. Because no matter what A, B belong to G, B minus 1 is equal B minus 1, A is equal to A. This means that the only conjugated element of the element A is the element A itself. Now, an element of a group belongs to one and only one class. Now, we will prove this later on. And another important result is that two elements of the same class have necessarily the same order. This means that if I have two elements that are conjugated of each other and A power n is equal to identity, then necessarily B power n is equal to the identity. So I will leave that to as an exercise later on that we will solve in class. And now I will prove that one element belongs to one and only class. So for this, it's enough to prove that if the elements A and B are conjugated, and the elements A and C are conjugated, then the elements B and C are conjugated, and then all the elements A, B, C are conjugated of one and the other, and they belong to the same class. So if A and B are conjugated, there exists an element S such as A is equal to S, B, S minus 1. If A and C are conjugated, exists an element S prime such as A is equal to S prime, C, S prime minus 1. Now I will express B as function as A by multiplying here at the left by S minus 1 and on the right by S. So I get that B is equal to S minus 1 A S. Okay, and now I will replace the expression for A here inside of this one. So I get that B is equal to S minus 1 S prime C S prime minus 1 S. Okay, now I can re-express this the following. So this here is S minus 1 S prime minus 1 S minus 1 S prime minus 1, because when you take the inverse of a product, then you inverse, okay, the product. So this becomes S prime minus 1 multiplied by S minus 1 minus 1, which is S. Okay, so if this is an element here, I call this the element S second, it's an element of G. Okay, so this would be S second C S second minus 1. So B and C are conjugated. And all the elements then A, B, C are conjugated of each other and they belong to the same class. And now I will give an example. Okay, for example, the group C3V of the symmetry of the equilateral triangle, the point group, which contain the element E, C3, C3 square, sigma 1, sigma 2, sigma 3. So if I want to construct the classes for this group, so the first class would be the neutral element. E forms a class by itself. Now if I want to construct a class of elements that are conjugated to C3, so I have to form all the product C3 S minus 1, where S is an element of G, and see which are the elements, okay, so that are conjugated to C3. So if I take the identity, of course, this is C3. Okay, so C3 is conjugated of C3, this is normal. Now if I take the element C3, 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 C3 minus 1, so C3 and C3, so this is C3 square. C3 minus 1 is C3 square. Okay, why? Because C3 square multiplied by C3 is equal to the identity. So this is C3 minus 1 is C3 squared. So C3 square multiplied by C3 square, so this is a rotation of 8 pi over 3, which is a rotation of 2 pi over 3 plus 2 pi and 2 pi over 3, so this is C3. Okay, so until now we just found the element C3. Now if I take C3 sigma 1 minus 1, sigma 1 minus 1, this is sigma 1, because sigma 1 multiplied by sigma 1 is equal to the identity, because when you make 2 times a reflection, okay, then you get the neutral element. Okay, now so C3 multiplied by sigma 1, I have to look at the table. C3 multiplied by sigma 1, okay, so C3 multiplied by sigma 1, so this is equal to sigma 2, so it's equal to sigma 1 multiplied by sigma 2. Okay, sigma 1 multiplied by sigma 2, I look at the table here, so this is equal to C3 squared. Okay, so C3 squared is a conjugated element of C3. Now if I repeat the same process here, sigma 2 C3 sigma 2 minus 1. Okay, so sigma 2 minus 1 is sigma 2. Okay, so C3 multiplied by sigma 2, C3 multiplied by sigma 2 is equal to sigma 3, so this is equal to sigma 2 multiplied by sigma 3. Sigma 2 multiplied by sigma 3 is equal to C3 squared. So same thing. I have to consider here sigma 3, C3, sigma 3 minus 1, and then I will get sigma 3, C3, sigma 3, which is equal C3 multiplied by sigma 3 is equal to sigma 1, so it's sigma 3 multiplied by sigma 1. Sigma 3 multiplied by sigma 1 is equal to C3 squared also. So the only element conjugated of C3 is C3 squared. So C3 and C3 squared form a class. So the second class of this group, okay, would be C3 and C3 squared. Now if I want to get another class, so I consider an element that don't belong to these two classes, for example sigma 1. And I repeat the same procedure, and then I will find sigma 1, sigma 2, sigma 3. So these three elements are conjugated of each others. And this group has only these three classes. Okay, so now a fast check, you can check if your result is correct, and you can use these properties to determine the classes also in some simple cases. So for example, in general, so rotations and reflections belong to different classes. So for a point group or a symmetry group, okay, rotations and reflections belong necessarily to different classes. So elements of different type belong to different classes. And another property, in order to check if your results are correct, is to use the property of the order of the element of a given class. So the order, like I said, the order of the elements of a class is the same. So for example, for the class C3, C3 squared, the both are order 3. If I have C3 cube, this would give me the identity. If I take C3 squared cube, I will also get the identity. Okay. Now, sigma 1, sigma 2, and sigma 3, they are all of order 2 here. Okay. And now I will define the notions of invariant subgroup. So if H is a subgroup of G, then if I form the ensemble of elements SH S minus 1, this means that I multiply all the elements of H at the left by S and by the right S minus 1. So this ensemble of elements form also a subgroup of G. So this property, we can prove it. Now, if SH S minus 1 is the group H, then H is called an invariant subgroup. This means that no matter what element A belong to H, if I make SA S minus 1, I get an element B that belongs to H. Okay. And now I will define the notion of isomorphism and homomorphism. So let G and G prime be two groups. We call homomorphism an application from G into G prime, such as to the element A in G may correspond the element A prime in G prime, A prime equals phi of A. Now, no matter what two elements A and B belong to G, phi of A multiplied by B is equal phi of A multiplied by phi of B equals to A prime multiplied by B prime. This means that no matter what two elements A and B belong to G, if in G C is equal A multiplied by B, then in G prime will correspond to the element C, the element C prime, such as C prime is equal A prime multiplied by B prime. And homomorphism respects the table of multiplication. Okay. But to each element A prime of G prime can correspond several elements of G. Okay, for example, for an element, a given element A prime can correspond to element A1, A2, and A3 in G. So in general, the homomorphism is not a bijective, application. If the application is bijective, it is called isomorphism. So two groups that are isomorphic have the same multiplication table. For example, the group of permutation of three elements and the group of the symmetry of the triangle are isomorphic groups. To each element of symmetry, we can make correspond a given permutation. Okay, so two isomorphic groups are identical from the point of view of abstract group theory because they have the same multiplication table. We can define a group by its multiplication table, even if they correspond to two different types of elements, for example, permutation and symmetry operation. In these two cases, from the abstract point of view of groups, they are considered as the same group because they have the same table of multiplication. So as an example of homomorphism, we'll consider the group C3V, that we considered before, and the group of two elements, 1, -1 here. So these two groups are homomorphic. There exists an homomorphism between these two groups. So if we make correspond to the elements E, C3, and C3 squared, the element 1 in G prime, and to the elements sigma 1, sigma 2, and sigma 3, the elements -1 here in G prime. So this application forms an homomorphism. So how can we prove that? We can prove that by verifying the multiplication table. So for example, I will take an example here. For example, is phi of C3 multiplied by sigma 1 equal to phi of C3 multiplied by phi of sigma 1. So phi of C3 multiplied by sigma 1, if I look at the multiplication table here, so C3 multiplied by sigma 1 is equal to sigma 2. So it's phi of sigma 2, and it's equal to -1 here. And phi of sigma C3 multiplied by phi of sigma 1 is 1 for C3 and multiplied by -1 for sigma 1. So it's equals -1. Now if I take another example, phi of sigma 1 multiplied by phi of sigma 2, is it equal to phi of sigma 1 multiplied by phi of sigma 2? So phi of sigma 1 multiplied by sigma 2 is equal to C3 squared and phi of C3 squared here it's 1. Okay. And phi of C3 multiply phi of sigma 1 multiplied by phi of sigma 2. So phi of sigma 2 of sigma 1 is minus 1. And phi of sigma 2 is minus 1. So it's equal to 1. So an homomorphism respects the multiplication table, but to a given element of G can correspond to a given element of G prime can correspond multiple elements of G. Now an isomorphism not only respect the multiplication table but also may correspond to each element of G a unique element of G prime. So they have both the same multiplication table.